introduce our tutorial on dealing with uncertainty in decision-making models. It will be given by Johannes Royset. I tend to say it in the French way, Royset, but it's okay? Okay. Royset. He was very, very nice. We are especially grateful because it was a last-minute change that Roger Wett unfortunately could not come. And Johannes was very kind in agreeing to give another talk on top of his plenary that he will give, and actually two tutorials. And then, well, thank you very much, and your turn.
So good morning, everybody. And thank you to Claudia and all the organizers for putting together this. Haven't seen much around coming late last night, but everything looks fantastic. I would like to acknowledge these slides is also developed together with Roger Wett. So even though Roger could not come, you definitely see that he will be here with us in some sense. Through these slides, which we worked on together. Okay, so of course, as you know, there are many advanced subjects one can talk about in stochastic programming, and there's great depth to the field in many areas. I'm going to touch on some of those, but this tutorial is primarily an introductory one. I'm not going to get into the most advanced things, particularly in the beginning. My main focus is on why should we care about stochastic programming? What is the fundamental things we can learn from adopting stochastic programming models, okay? So some of you might have seen these type of examples before, particularly what I have in the beginning, but I think at least for new people to the community, it's important to really, before you get into the mathematical sophistication, to really understand how these things can be beneficial. And of course, this is essential if you are going to become a practitioner of stochastic programming, and you need to convince your boss or some sponsor that it's worthwhile to get into a modeling effort of this kind. Okay, so I'm going to start with a very simple example about a product mix situation, and this is something that you can find in many different businesses. Here, I'm going to talk about furniture for no particular reason except that the part of Norway I'm coming from, there's actually a big furniture business, a lot of furniture businesses. But whatever the situation might be, we have somebody that needs to make a decision about 4 different products to make. Each of these products is going to give you some sort of profit. And what is the profit? Well, per unit profit, if I make the first, this is some sort of dressers, the first dresser, I'm going to get $12 per unit I make. The second, I get $25 per unit, so that's a pretty good unit to produce, it seems like. 21 for third, and 40, so that seems to be the one that I get the most profit from. So a simple for-profit analysis will end at this point. One would look at, well, it looks like it is the 4th type that is most profitable, and we will simply produce all of those. So in an unconstrained world with no complications, this seems to be the first thing one will do. Okay? But of course, we would like to try to account for other factors as well. And as in most businesses, this business here is constrained. And in particular, I hope it's possible to see a little low here, but there are 2 constraints in this business. Apparently, to produce these dressers, one needs some sort of carpenter work, and there's some sort of finishing work. So 2 types of work. So maybe there are 2 workshops that are working on this to maybe to complete this job. So these things take time, and unfortunately, I have limited amount of time, or maybe this is in terms of the number of people I have available in my workshops. So in terms of carpentry work, I have DC hours available. And how many hours do I use? Well, if I produce 1 hour, if I produce 1 dresser of type 1, TC1 is the number of hours it's going to take me to make that one dresser of that one type. And the story continues, similar for the second one, third and fourth. And if I sum all those things up, I'll get the total amount of hours I need to produce this X, 1, 2, 3, and 4 dressers, okay, number of dressers. So certainly that should be less than or equal to this D. And there's a similar story for finishing, where potentially different numbers, of course. Okay, so all seem good so far, and there should be no complication. If you've seen an optimization model, which I think most of you have done, this would be maybe among the simplest ones that you've seen for sure, some sort of a knapsack model. And of course, this is easy to solve in any linear programming solver. You can maybe even attempt to do it by hand. And the specific numbers that we might take is, well, here are the total number of hours we have for carpentry finishing work. And these numbers here, they were the hours I needed per unit. So 4 hours I needed to produce 1 unit of type 1. Okay. Okay, so if I run this into a linear programming solver, this is the optimal solution I get. For the first type, I should produce something like 13,333.333. I put nothing of type 2, nothing of type 3, and then, what is it, 67 or something like that of the fourth type. Okay, a novice to modeling might immediately get the following concern. We're talking about dressers, and dressers, at least last time I heard, cannot be produced in fractions. You know, it needs to be an integer number. Okay, so there might be a first sort of modeling concern that might come up. Here, I think it's an important thing to realize that one shouldn't overestimate oneself in terms of potential to influence a decision maker. I think many of us, in some sense, are in the business of trying to influence decision makers to help them to make better decisions. But if you produce a solution and give it to your boss, it's important to realize that the boss probably is not going to take it immediately and implement it. What's going to happen is that it's going to be looked at, hopefully, and then put in a dress, on a shelf, and maybe the boss will go on and make his or her own decision. So this is some sort of a guidance, okay? So the fact that you get into the fractions here might not be as important, simply for the reason that the manager, your boss, is simply looking at the big picture. And what she might be looking at is simply that, there's 0 here and 0 there. So these are the two products that are now simply going to X. Okay? So these are the two product lines. Maybe I can simplify a lot of things by simply getting rid of this altogether. Okay? So your boss might be looking primarily at that instead of the actual numbers that he or she might have a better sense how we're going to do those. Okay? So that's one point to keep in mind, that often the takeaway from optimization model, including stochastic optimization models, is not always about the specific numbers, but it's more macro scale trends that can be extremely useful for a decision maker. Of course, this doesn't diminish the value of the analysis. It just shows that the analysis is often used maybe in a larger way that you might immediately think. On a more technical point of view, Jim talked about yesterday about integer variables, and of course, there are many important situations when one would like to account for integer variables explicitly. Here, I think is not necessary. Sort of a rule of thumb is typically if you're dealing with a number that's greater than 100, it is not really a big deal to just keep them continuous and then do rounding and never tell your boss about the fact that you didn't explicitly account for integrality. Okay, and by the way, back to these numbers, this is the profit that is predicted by this particular production plan. Okay. So the question is, how did we get these numbers, by the way? you might wonder. In particular in a real setting, in a real-world setting. Unfortunately, these are rarely given to you, okay? Often, you are the one who has to figure out what numbers to put into these optimization models. And naturally, the question becomes, what would be an appropriate number, okay? Or if there is even an appropriate number to put in. There are many, many situations where we cannot get around the fact that the numbers that we want to put in for parameters are simply not there. We might have some data, but it's data about something else, or maybe it's data about the parameters, but it's not like it's always just one number. Maybe there's a variability in these parameters, as we have observed in the past. So it seems like when we need to account for uncertainty some way or another, of course, this is not a surprise considering where we are. But there are, of course, some situations where the numbers are indeed given to you, okay? I personally experienced one situation where actually there's absolutely no need for stochastic programming. Let me give you the situation that I encounter, and maybe other people have similar other experiences. Several years ago, I was involved with helping decide which military bases in the US should be closed, which one should be invested in, and which one should have soldiers moving from one to another, how and when this should be taking place. Of course, this is a highly contagious decision, meaning that not contagious, contentious decision. And of course, what is the political issues, jobs at stake, okay? In that situation, what the Pentagon did, basically develop a calculator that calculated exactly how much it will cost to move one soldier from Texas to California, how much it would cost to do this and that. And that was a calculator that was approved and stamped OK to the way top. And these were the numbers that are going to be used in any analysis to make decisions about this, okay? So that was a situation where somebody had approved all the numbers that were going to all the optimization model associated with all these decisions that were going to be made, okay? So in a way, then everybody played with the same rule book, okay? So that could be a situation where there's no uncertainty, but obviously this is a highly constructed, it's almost like a game. Everybody agreed the rule of the game, and then there's no uncertainty to some extent. Of course, if this was a good rule book or not, and of course, in reality might not always correspond to this, but everybody agreed to play with those rules so one can make comparisons and things like that. So that would be a situation where maybe uncertainty is not important, okay? But I think in most practical situations, there will be some element of uncertainty that needs to be accounted for. And let's take a look at here, for instance, in this business setting, where certainly uncertainty is important. You might have a situation where, for instance, the times of producing these different products might be unknown. Maybe somebody's a little slower, somebody a little faster. There's mistakes taking place during the production process. Whatever might happen, these T's might be unknown. Okay. So I'm going to use boldface for random. Okay. So this T is going to suddenly become bold, indicating that this is a random variable. So this maybe there's a nominal value that is added to an eta that is some sort of a random variability that's added to it. Okay, to make life a little simpler, and by the way, the same thing is for the D's. These were the capacities, how much we had available of these different hours in the different categories. Just to make up a story, we have 4 different values that these D's can take on, and 4 different values each of these T's can take on. So that gives me 10 random variables. Each can take on 4 different values. So if I look at the whole set of all possible scenarios, I will then have something like 4 to the 10, so something like 1 million possible outcomes that can happen. Of course, this is just constructed for the sake of illustration. This example, generally speaking, one could have a lot of scenarios. And in fact, one of the core challenges in stochastic programming is, of course, related to that we often would like to look at a very large number of scenarios, because after all, the future might come in many different colors and flavors, and it will be important to try to capture many of those, at least it seems like, at the outset. Here, capturing 1 million different is, of course, not all of the possibilities, but at least it's much better than just thinking about one possible future. Okay, so now, how we have some modeling work to do now. Because now I'm saying that, okay, we certainly would like to satisfy these demands. And by the way, here I'm introducing a little bit more matrix and vector notation. So this D is the vector of both of the carpentry finishing. The T is the whole matrix of times, etc. But the main thing is now, what happens if I somehow make a decision about X? Okay, I would like to produce this and that. And I do that before I know exactly how much time it's going to take and how much hours maybe I have available. And when these things get realized, I might very well find myself in a situation where the total time that I need in one category, being in finishing or being carpentry work, exceeds maybe the time I have available, which itself could be random, but now have been realized to an unfortunately low value. So now we have a problem, of course. This is, in the original model, we're basically in the infeasible domain, right? But anybody working with an aggressive and energetic business leader, you will hear that there's no such thing as infeasible, right? One will simply pick up the phone and make it work. And in this case, pick up the phone is to pick up the phone to maybe your nephew that happens to be out of school that can come into the shop and help working. Okay? Or maybe it's a question of overtime. Okay? So basically, this thing about the infeasibility that often in optimization we look at very rigorously. Of course, in a practical setting, often there's flexibility. And when we think about models that will capture this flexibility, and here's one example, of course, in a very simple setting where we're going to capture it by overtime, or we can think about this as overtime. But overtime, it doesn't come for free. You have to pay your nephew something. And how much should we pay? Well, suppose the cost per actual hour is Q. Okay? Q for the carpentry work and QC for the carpentry, QF for the finishing work. Okay. So now we have the following situation that CX, that was how much money we were making. But now, unfortunately, we need to subtract of QY, where Y is the amount of overtime hours we need. And let's see how Y comes up. Let's focus on the first row here. So TX, that's the amount of time that we are spending. D is how much we have available. But if I move Y over, you see this is some sort of slack variable that can help us. So if Y is positive, it will help us to satisfy this constraint. But whenever Y is positive, we pay a price, presumably Q is a positive number. We pay it up here, it reduces our profit. But now there's this issue that we don't know the future. So we had to make this decision before we know what's going on. So the situation is now simply that we have 1 million possible futures, and how shall we somehow make a decision before we know that? Of course, there are more than one way of doing it, and we're going to talk about some of them here. And one possibility would be simply look at what would be my expected cost if I make a particular decision. Okay, so let's look at that. So if I pick X, okay? Now all these TX has been decided as soon as I have realized all that. So let's make sure I make straight out what is the decision process. I'm going to make a decision about X. And then I'm going to learn exactly what the times that's going to be taken. Maybe the next day, reality hits, and I'm going to learn how much time it's going to take to make these things. And I'm going to realize also how big is my D, what is the capacity of my plant this particular day. And now I will make my adjustment with regard to overtime. So I'll call my nephew, bring in the number of nephews that I need. That will cost me money because this is Y, is the amount of hours they are bringing in. And I will then have a reduction in my profit. But since I'm going to decide on how many of my cousins I'm going to bring in, after I've learned the exact amount of the times, the exact amount of the demand, or sorry, the capacity, I guess, these Ds, I'm actually, at this point, before all of this is taking place, I have the luxury to think about this in terms of one variable, Y, in each of these scenarios. So that's why I have going to have L different. L is all those, the million different scenarios I have, going to have one per scenario. So the initial decision, X, is going to be something that I have to stick to, but I have developed different Ys for the different scenarios. You can think about this in terms of contingency plans. If this scenario takes place, the first one, say, I'm going to apply Y1. This is the number of hours I'm going to pull from the street. If scenario 2 happens, I'm going to do Y2. Okay, so I have a bunch of contingency plans in my drawer that I'm going to pull from. So now, what is the expected cost that I'm going to have viewing it from the current point in time before all of this is taking place is then, of course, the money I'm making from selling these things minus the expected cost to have for all of this overtime. And that's why these P's come in, and this is the probability of scenario 1, probability of scenario 2, etc. So this decision Y is what we call a recourse decision. So something that we try to do to mitigate the situation after we learned something more compared to where we are today. So this is the setup. And by the way, from our technical point of view, not much have changed. Because if you look at this optimization problem, of course, it's still a linear program, and we can give it to a solver. But maybe before I do that, let's just put in a little bit more general notation that will allow us to talk about this a little bit more efficiently as we go forward. So this capital Xi is going to be this set of possible values of the randomness. In our case, I guess the random things were these noise, these errors or these adjustments to the times. It's going to be some of these zetas, which has to do with how the amount of hours we have available changes potentially. And P is going to be the probability of these different type of scenarios. We had 1 million of them. Then it's convenient, particularly as we start going to do a little bit more analysis, to write out what is the recourse function. So what is that? The recourse function is if somebody made a decision X already, and somehow I know psi, so I know exactly what this level of uncertainty is, so the uncertainty has been revealed to us. What is the additional overtime cost I have to pay? Of course, in our situation here, it's pretty straightforward to figure out, because if I know X, I know psi, it's simply arithmetic exercise to figure out how much overtime I need, maybe 0 or maybe something. But we can write it in this maybe excessively complicated way as an optimization problem. So we certainly want to minimize our overtime costs, or maximize the minus of it, if you like. And this is by trying to find a Y that brings this as large as possible. But of course, Y will then just be just enough so I have equality here. And of course, what I'm really interested in is that expected overtime cost, because of course I will not know psi when I'm making the decision, which is written here. And in this case, is simply I just average over all those scenarios. So I then get into what we call the equivalent deterministic optimization problem, where I, in a way, have hidden everything of these complications about overtime in this expectation of Q. So this is a deterministic optimization problem. So then we actually get to this following kind of paradox, that in stochastic programming, there's nothing about computer programming in stochastic programming, at least in the name, and there's nothing stochastic about stochastic programming in the sense that this is certainly a deterministic optimization problem. Okay? So that is something that, you know, the very good reason to call it stochastic programming, but it's important to realize that a stochastic program, for instance, like this, is simply a deterministic optimization problem, of course, involving certain complicating factors, particularly involving uncertainty. Okay, so we have an optimization problem. So much of this tutorial is going to be about analyzing properties of this, and as we go forward, we're going to talk about more mathematical properties, about this is a nice optimization problem, what can we do with the algorithmic procedures and things like that. And we're going to see things sort of talk about convexity and things like that, non-smoothness is going to become important. But before with that, why don't we simply solve it now as this large linear program that I wrote down before, you know, I introduced all this notation about Q. And this is, even though, remember, I had 1 million variables on top of those 4 that I had from the beginning. So it is a sizable linear program, but, you know, I think, you know, most of your laptops can handle 1 million variables in a linear program these days. So we can still do it, and we get an optimal solution, and here it is, which has a certain profit. Okay, so the first thing is realize that this, what are these numbers? Well, these are numbers from a model where we made a lot of effort to try to account for 1 million possible futures, okay? So somehow this x that we have here is one that is good in the sense that it maximizes the expected profit, okay? Maximizes the expected profit over those 1 million possibilities. So in a way, inherently, this seems to be something good. So it is in somewhat of a robust solution. But let's make a comparison. What was the initial solution we got when we solved that simple deterministic optimization problem that we started out with, where we didn't account for uncertainty? And this is where we see some significant differences. So if you look at the numbers up here versus down here, the most striking here that we have both product 2 and 3 are considered not viable here, while up here, actually product number 3 is certainly viable. And this will be the first thing that your boss will look at, because they say, look, actually, we shouldn't ax product line number 3. There seems to be a situation where we would like to produce product 3. So from a strategic point of view, you now have a completely different and I think much more informative message to give your boss, that there are actually situations where product 3 should be produced. So if I relied only on a deterministic tools and so relied simply this as my guidance to my boss, I might potentially have made a bad decision. But by the way, how do I know that this is not a good decision? Okay, so if I make a comparison with this and this, well, these are just numbers. Why is 3 should be included or not? Let's look at the numbers. Okay. If I look at the profit up here, on average, over those 1 million possible futures, I make about $18,000. This X here, even though I didn't, when I optimize for this X, I didn't think about uncertainty at all, right? This is something that came from a completely deterministic setting. But the moment I have an X, whatever, maybe something you pull out of thin air or something, the current thing you're doing, whenever you have an X, you can always assess it with respect to an uncertainty model. For instance, these 1 million scenarios. So for instance, with that particular plan here, this XD, I can always compute what is the expected profit across these 1 million scenarios. And that's really what we should do, right? We should say, okay, I think these are the 1 million things that might happen to me. And I would like to see, well, this particular decision, is it good or not? Okay. And I can do that, I can take that x, put it in to my formula for the expected profit, and it turned out that it's only $16,000, okay. So even though you might say, well, didn't we talk about a profit when we, long time ago, when we started out with this business, we computed this, we got an objective function value, which was, I think, was something like 18,000 actually. But what was that number? That was the profit if all those t's, all those d's were actually correct, okay? But now we came to the realization that actually those times and those d's are not really written in stone as we might have hoped, but indeed they are random, and we have kind of accepted that we are dealing with a million different futures. So under the million different futures, what we are looking into is that if we make this plan, this is what we're going to profit on average, okay? Which is certainly worse than that. So from this, there's no way around the fact that the plan we got using this model, accounting for uncertainty, is indeed better. And of course, it doesn't take much to realize, of course, one cannot do better than this if we're talking about this million scenario, because this was indeed the one which maximizes the expected profit, okay? So this will be the highest you can get when you assess profit in this way. Okay. So I think this is summarizing what I just said, that if I do the deterministic setting, I get a solution that might not even point in the right direction, okay? Is qualitatively off in some sense. You might think, did we really fiddle with this number a whole lot, to get this thing to work out exactly the way, because we want to give a sort of a make a point or something like that. When Roger Wetz cooked up these numbers, this was the first number he tried. And in fact, we are not the only ones that cooked up these type of numbers. There's a very nice article by Julia Higley and Stan Wallace in Interfaces quite a few years ago. We're talking about a similar situation where again illustrate how one would get a completely different insight if you deal with a model of uncertainty. So that's a paper that is definitely worthwhile reading. Okay. So I'm going to mostly leave this simple introductory example now, and maybe for a moment just pause and look at the bigger picture that we have in this story here. A student of mine once said, stochastic programming is terrible because you need to know 3 areas of mathematics. You need to know probability and statistics, which, by the way, he counted as 1. You need to do optimization, and you need to know real analysis. And from his perspective, this was a negative, more to study. But of course, there's much truth to that. Stochastic programming is a tremendously rich area. I think for us working in the area, I think that's one of the fascinations, is that because it draws on so many different aspects of maths, which makes it a very challenging area. Of course, it makes it also maybe somewhat challenging to teach and explain and things like that, but I think we're getting better at that. But let's talk about what are the key tools that will come in to a stochastic programming setting. Of course, optimization is going to play an important role in all its various forms. In fact, this is, in a way, our backbone. You've seen that quickly, even in this simple, I would say, Mickey Mouse example that we had here, it's simply really already there a very, very large-scale optimization problem. We had more than 1 million variables. So that didn't take long. So certainly we quickly get into the business of need of maybe take advantage of the special structures arising here. And for those who pay close attention, indeed, this linear program was very, very special. It was not a general, it was a very special linear program. So one can imagine there can be special algorithms. And I'm not going to talk too much about algorithms today, but one can imagine that one could certainly develop, and people have developed very good decomposition algorithms, like the L-shaped method and similar. Variation analysis is going to be the foundation in terms of all analysis. So as you know, variation analysis, of course, is the extension of convex analysis into non-convex problems, extension optimization into a broader class of problems, equilibrium problems, and all these type of things. And this is things we need, so extension of smooth calculus into non-smooth calculus. And of course, these are all things that's going to become very important, in particular, even in this tutorial, where we're going to see, if I want to say something about this optimization, but we need to fall back on variation analysis as the key technical tool. Of course, probability and statistics is going to become very, very important, in particular, as we're going to try to develop what are appropriate models of the uncertainty that we're facing in a real-world situation. This is something that I want to talk more about on Thursday, so I'm not going to say too much about that here. And of course, there might be unavoidable some element of function analysis. You see that towards the end of the talk, you see that stochastic programs quickly get you into the business of infinite dimensional optimization when you have a situation where you don't have a finite number of possible outcomes. Okay. So, by the way, as we go forward now, I think there's going to be a break halfway through, I think. Is that right? I hope you guys keep up with the time. But in the beginning, I think the first half, we're going to focus primarily on modeling, I think, and then they're going to be a little bit more technical towards the end, but maybe even to end the first half. Okay. So let's now maybe try to bring this up to a little higher level, get away from the specific of this particular production example that we worked with, and say that we basically find ourselves in a situation that we might, at the beginning of the day, start with an example of an objective function, f naught, that we want to minimize over some feasible region. Okay? But then, as we talked about, we might quickly find ourselves that with the moment we start writing down the objective function, writing down the set of constraints, we might find ourselves there is some parameter here called xi, could be a vector, big vector potentially. And this xi simply, we are not sure exactly what are the parametric values. So these are uncertain parameters that we need to, of course, make up our minds about. So how should we handle this situation? Of course, the easiest thing, if you have the luxury, would be to say, look, I don't know this demand tomorrow. Why don't we wait until tomorrow morning, where we might very well know, at least roughly, or maybe very accurately enough at least, the demand, and we postpone a decision to that point in time. So we know the decision, know the psi at the point of decision. You think about this as like a wait and see approach. And those of you that are a little bit maybe last minute persons in life, you will sympathize with this approach, right? You put things off a little bit, maybe I'll learn something more, you put it off the decision. Of course, this is something that could make sense in some situations, but often in many others, it's simply not feasible. You need to hire workers, you need to acquire raw materials much before you know the demand. Of course, just-in-time principles and things like that, of course, is in a way try to get close to this wait and see, or to wait as long as possible to just get exactly what you need. So of course, from a business perspective, one would like to get close to this, but it's not always possible, okay? So what we need is some sort of here and now solution. We want to make a decision before we have realized the uncertainty. And why don't I give you another example? It's a classic example called the news vendor problem, which is another situation where uncertainty is important, and is one where you can kind of relatively easily analyze in a few minutes what's going on, so it's very instructive. And by the way, for the younger generation here, of course, the younger generation have no idea about what a news vendor is, but you can think about a movie from the 1950s where there is a child standing on a train station selling newspapers, those things of paper, that nobody's reading anymore. Of course, what is the main concern of the newsboy? The newsboy has to go to his boss in the morning and ask for a certain number of papers, and has to pay up front, okay? So he's going to ask for 100 papers, pay up front, and then go to the train station and start selling. And here's the issue. If that's the if that's the day after Brazil and Argentina played in the Copa America or something like that, everybody wants to get the newspaper. But if it's on any gray Tuesday, maybe nobody will get the newspaper. So the question is really what the demand is going to be, and the newspaper has to make a decision about how many newspapers to buy before he knows the demand. So here's the story. So we have a perishable good, maybe it's a newspaper. We don't know the demand for it. It's psi, it's a positive, a non-negative number. We're going to order it. It costs the newsboy $10 per newspaper, pretty expensive newspaper. Then you're going to get on the train station, you're going to sell this newspaper. Y is the amount he's going to sell. And he's going to, he's planning on a profit of $15, meaning he's going to sell it for 25. Okay, maybe this is cents, by the way, more appropriate for the 1950s. Okay, so how much money are you going to make? Well, let's see what the formulas we can come up with. CX with a negative in front, that's certainly how much the newsboy has to pay out up front, right? And this, what is this? C plus R, 10 plus 15. That's how much money I get per item I'm selling, multiplied by the number I'm selling. So this is how much money I'm making. This is how much money I paid up front. So this is the total, excuse me, is the total revenue. Of course, X should be a non-negative number. And what is Y? Y is how many I'm going to sell. And certainly I cannot sell more than X. That was how many I acquired. But psi is also my limit. Psi is how many I can sell, how many customers I have. So whatever smaller of X and psi, that will be the number I will sell. Okay. So as a newsboy, my goal is to find what's optimal X. Of course, the main problem here is that I don't know psi. It's indeed uncertain. Well, one possibility is I can simply guess the future. I look at the weather, snowy, not snowing, and I'm going to make a guess about how many maybe psi hat. Okay. I can certainly solve this optimization problem, and in fact, what I'm going to do, if psi hat was 75 newspapers, it's easy enough to figure out that actually exactly what I'm going to do is to decide to acquire 75, sell 75, because I assume the demand is 75, is going to sell all of them, I'm going to be left with none. And I guess how much money I'm going to make is easy to evaluate from this formula now. The problem with this, of course, is we don't know really how good this is. It doesn't seem necessarily to be a good plan. What if we find ourselves in a situation where the demand is not 75? Okay. What's going to happen then? I'm going to return to that. We'll see how bad 75 actually is. We're going to try to do a little bit better by developing a model that accounts for uncertainty. Okay. But before we do that, we might do what we call scenario analysis. And this is, of course, some of you might have taken a course in deterministic optimization. You have heard about sensitivity analysis, sort of perturbation analysis, things like that. So you might say, well, maybe I can learn about uncertainty in the following way. Let's take a whole bunch of psi's. Okay? For each of those psi, I'm going to solve this optimization problem with that particular psi. So I'm going to say, okay, what if the demand is 25? What would be the best thing to do then? What if the demand is 45? What's the best thing to do then? And I go through the whole list of maybe a bunch of different psis and find the best plan in each of the cases. And you might feel proud of yourself by going through that because, well, I'm kind of accounting for uncertainty, you say, because I'm trying different psis. But what's important to realize that that if you do that in this particular situation, in many practical situations, it's going to be difficult to construct an actionable plan from the analysis you just did. Because look, what's happening here. If I do psi equal 10, 20, 30, up to 150, I solve this for each of those different psis, what I'm going to get? Well, remember, in this particular model, the optimal X is actually whatever psi I'm picking. That means that in the first scenario, I'm going to get a recommendation to buy 10 in the second, to buy 20, etc. So suddenly, in all this scenario analysis, I get a whole lot of different plans, and they're completely different. So it's not easy to how I can sort of reconcile them into an actionable plan. After all, I'll need to make one decision. So it's not clear how one reconcile them. Although this idea is somewhat fundamental, and we're going to return it later. We're going to talk about the progressive hedging algorithm. So we have a relative limited use. So it's important takeaway that the fact that you look in different scenarios and optimize might not necessarily tell you much about the real world situation. You kind of need to account for what is the decision process that's going on in your particular situation. Okay, so let's make this a little bit more concrete and say a little bit about, so what is this demand? Well, maybe I've collected data over many, many years about how much demand I have on this platform. And maybe from that, I can generate a probability distribution of the demand, and maybe it is this one. Of course, there's maybe not all days are created. Mondays are different than Tuesdays, etc. So one has to be really careful when we develop demand distributions like this, of course. And I'm going to talk more about that on Thursday. But for this talk, assume that we are relatively happy with a demand distribution that looks like this, which is actually log normal with a mean of 90. Okay. So H is going to be the cumulative distribution function of this particular log normal. So now we can try to do the same thing we did in the earliest example, and we can try to maximize the expected revenue. Okay. So how would that come out in this case? Well, it will be very similar as before. We have a certain cost that we're facing up front. There's nothing deterministic about that. We know exactly how much we need to pay. But the complication comes from how much we are making. And remember, we're making C plus R per newspaper we're selling, and Y is going to be the newspaper. And here what we're going to realize that we are going to, the amount we're going to sell is something that is going to be decided after we learn the demand. So imagine that we decide on X, we work on the platforms, and maybe this is fast forward very quickly, the morning is finished, and yes, there was a demand of something, okay? So, and that is the point where you're going to account for how many newspapers did I actually sell. And that's going to be my Y, and because I'm going to account for Y after I've seen the randomness, I'm going to call it a Y of psi. And what is Y of psi? Of course, it is a certain number between 0 and the smallest of psi and X. And of course, we will probably like to sell as much as we want, so we're going to be tight on the upper side. So this expectation, again, we can think about that as an expected recourse, and using this Q notation of what's inside here. So that's just written out here. And of course, mathematically, in this particular situation, as I said, Y will always be incentivized to go up towards its upper bound. So the formula for Q is simple enough to work out. If, for instance, in a situation where the demand is low, less than X, I will certainly just sell psi. If the demand is high, then I'll be limited by X, and I will simply sell X. So this is how much I will make. So in this simple case, at least if this cumulative distribution function is collaborative, I could even evaluate this integral explicitly. So if you're taking some, calculus class, which I know all of you have done, one can say that, okay, I have an optimization problem, I want to maximize. Maybe you can take naively to take the derivatives that are equal to 0. In this case, that's going to work. Of course, there's some technical concerns about doing something like that. We want to return to that later, in particular things like the non-smoothness of these functions. But in this case, one can actually indeed take the derivative, you know, basically this Leibniz rule, because x shows up here. So Leibniz rule will give you the derivative of this. You can set equal to 0. And a tiny bit of algebra, you will find that the optimal, indeed, is the quantile, so the inverse of the cumulative distribution function at a particular ratio that depends on how much the profit and how much you buy it for in the morning. In this case, with the numbers that I have picked, the ratio is 0.6, so we get this number here. So here is the cumulative distribution function of the demand, and we get this. There seems to be a slight discrepancy here. I think it's 92. It's not 99. It's 92.2. Okay. So 92.2. So that is the optimal purchasing amount in the case where the demand is log normal. Okay. So this seems, first of all, is a different thing than 75 that we played around with earlier. But we can also try to look at this more specifically. Here I plotted the objective function. So what is this? It's simply just this whole objective function as a function of x. And since I can compute this expectation explicitly in this case, this is easy enough to generate. So here you have x on the first axis, and this is my revenue, expected revenue. And indeed, the optimal, this 92.2, that is what we're seeing up here. So even in this picture, you see it's a strictly concave function. So in fact, this solution is even unique. By the way, now this may be a good time to see how much profit we are making with this decision, which is like 1084. If I did 75 as a purchase order, I get a profit of about 1,000. So certainly 75, I would have lost some money on average. Okay, no doubt about that. If I have a plan of 75 or whatever other plan that deviates from 92.2. Okay. So you might say, well, maximize the expected return. Is that really, we kind of took that as our goal, and we get improved results from doing so. But is that really the whole story? It could be a fair question to ask. And here's a picture that uses the number from the news vendor problem. Actually, it's a slightly incorrect picture, but it tells qualitatively the right story. It basically says if I fix a particular plan, say x equal to 72.2, purchase order 72, and look at what is the probability density function for the revenue. Okay? So don't take the expectation, just compute the full probability density. Okay? Then you're going to get this blue line. Actually, there's a probability mass at a certain point there, so this is kind of like an approximation. There's actually no probability density, there's a mixture. But let's ignore that for the moment. The story is the same. You basically see, if I make this plan, I'm pretty certain that my revenue is going to be around 1,000, plus minus a little bit. Okay? Pretty sure about that. On the other hand, if I'm getting to 92.2, which, remember, that was the one that optimized expectation, then actually there's more variability. You know, I'm going to get pretty high here, and that's what we saw earlier. But there's actually a significant possibility to get less revenue. This is the green curve. So there's a significant probability to make it even, it seems to even go negative here as a possibility, but whatever that might be, but at least very small, okay? Very small. So in fact, if you think about how financial advisors work, financial advisors often present you pictures of what could your future look like under different investment strategies. And here's the same story. We have different decisions X, and this is what we're looking at, the different, what could your future look like? So if I make this X, I'm pretty certain that I'll find myself with a revenue around 1,000. But if I pick, for instance, X equal to 132, then there's a huge variability, okay? There's huge variability about what I might face. So of course, as a financial advisor, for instance, you would like to figure out what is your client's stomach for this different distribution. Does this person like a large variability but potential huge profit? Of course, with this, you can have a potential huge profit more than 2,000. Or is this more a person that sleeps poorly at night under such circumstances, so you really like to have a narrow band, then maybe this would be a better decision. Okay. So it was important to realize that when you do expectation maximization, you're just doing one part of the story. There's more to it. More to it has to do with the full distribution, okay? And what is the distribution that you like to see? Of course, expectation is just one characteristic of the distribution. Here's the same story in terms of the distribution functions. But that basically gets me to a short comment about the decision criteria that I might want to have. So although I focus on expectations now in this small, simple example, the important takeaway is that that's not the only story one can adopt. There are many other possibilities, and I'm going to make some comments about some other alternatives. We talked about expected return. Maybe there's other things to think about with expectation, but maybe things like value at risk. You know, value at risk has to do with what's happening out in the tail potentially. Okay, and in finance, that is something that is popular to use. In engineering, an equivalent thing is called probability of failure. So the probability of exceeding a certain threshold. Maybe somehow you're very concerned about a particular threshold, or you don't want the probability of having something worse than that threshold occurring. You want that to be really low. So that may be another concern that you want to bring up. Then one might minimize in different measures. This is not measuring in the sense of measure theory. This is measuring in the sense of risk measures, deviation measures, measures of regret. And these are the things, of course, that allow us to account for risk averseness in various ways. And Professor Shapiro, in the next tutorial, will go into more details about these things. And I'll give a couple of references as well. And just make a quick comment about expected utility. So Van Neumann and Morgenstern wrote a very influential paper in 1943, which, of course, set the stage for a lot of developments in economics about how one should make decisions. And the story is, of course, one where one's going to take an expectation, as we did, but somehow you're going to have a utility function that distorts the quantity that you're interested in. Somehow, by doing that, if you distort it in the right way, you will be able to account for different type of preferences. So, of course, this will be studied extensively, but I just give you a word of caution. If you look at the book called Risky Curves by Daniel Friedman et al., is a very nice description of how expected utility often fails to capture preferences of decision makers. And I might have got an idea about what your preference was yesterday, but today, somehow, your preference has changed. So if I want to carry a utility function over to a new situation, it's very difficult to do that. And that has to do with how the human brain works, that you're thinking about terms of decisions in stages, what can I do about decisions? And that's really the key thing. If you think about how did we capture uncertainty in these two simple models, in particular the product mix one, we capture uncertainty in the following way. Okay, I might have a shortage of labor. I would then think about what can I do about that? Well, I will call my nephew, get in overtime workers. Okay, I will get in overtime, but that's going to cost me something. So that actually, I went into great depth to try to figure out what will I do if I get in different type of situations and what is going to cost me. So I actually had a model of what I'm going to do if things are going bad. So I thought about recourse actions. In a utility function setting, you don't think about that. And that's the main problem with utility theory, that you don't think about what you can do to mitigate the situation. You basically take the random variable, stick it in your U, at whatever that might be. Okay. Let me make a comment about robust optimization as well. So robust optimization, the word itself is a good word, but it's used in the optimization community for a narrow class of models that are of a particular type. And robust optimization models are of the following type, that we might have a similar setup as before, where I have some functions where they depend on a psi, that psi is unknown. And the fact that it's unknown needs to be captured in one way or another. And one possibility would be to say that psi lives inside a set U. And I'm going to look at the worst case value of psi within the set U. Okay. So it will be a worst case model among a set of possible parametric outcomes. Okay. So that is what called robust optimization. Of course, what I just talked about earlier in the product mix and the recourse model, of course, they are robustifying optimization models as well. But the historical reason why these particular classes are models called robust optimization. So in a way, you can almost think about this as a very, very special model of uncertainty. That you look at kind of the worst case within a set. You don't think about the probability distribution of psi, but you just look at the worst case value. So in that sense, it has a simplicity to it that can be beneficial in some sense. And it can also be something that in some very nice cases leads to significant computational simplifications where these problems can be solved in a very elegant way using convex analysis and things like that. Of course, our main challenge is that is hard maybe in some situations, and not to say all situations, to figure out what this set of uncertainty should be. And of course, the result will be sensitive to that. And in some sense, you might not account for the information you have about psi. Maybe you have some information about psi, you have some data about psi. That it's, if you only let that information inform you about the size of the set U, you might not fully account for that information in an effective way. Okay, we have say something about chance constraint as well. So that gets us into the business of probability of failure, value at risk, and things like that. Basically, imagine that you have a threshold. Maybe the threshold is 0. And I really like to see that this random variable, which indeed this is a random variable, so if I fix x, that random variable, the probability that random variable takes on a value less than 0 should be a high number. So presumably less than or equal to 0 is a good thing, and greater than 0 is a bad thing, so that's something that I would like to avoid. And society in some areas are set up in this way. In fact, you might be contractual obligations, the different policies, that there's really a hard limit, okay? And it's not like, remember we ran short of labor hours, so we called our cousin to bring in a little overtime. Maybe there's union rules that says there was absolutely no way that we can do more than that. So there could be a pretty hard constraint in some situations where this might be appropriate, maybe particularly is legal requirements and things like that. Unfortunately, these type of models, from a technical point of view, are quite unpleasant. And there's a lot of technical challenges dealing with this, which I'm not going to go into. I just want to alert you to the fact that these type of constraints are generally non-convex. So, and that might even be in a situation where this function f is convex in x for every psi. But there are convex alternatives. For instance, we introduced what we call the buffered failure probability, which is basically a conservative approximation of constraints of this kind that will preserve convexity. If f is convex in x, then such constraint can be modeled in a convex way as well. Okay. In terms of a couple of other things, stochastic dominance is another way to try to face this or address this situation that maybe we don't want to look at expectation alone. Remember I brought up the picture of the probability densities, and we made the story about, as a financial advisor, we might put up the whole distribution of our wealth in retirement and different alternatives to get a feel for it, because really it's the whole distribution really that we are faced with as we go into the future. So of course one idea would be to say, look, If I have one probability distribution, I guess, in this picture, one probability distribution, I have another one, maybe there's a situation where I can for sure say that one is better than the other. And that would be nice, at least to weed out some distributions and therefore some decisions that are certainly not good ones. Okay, stochastic dominance is a way to do exactly that. So I think this is the picture of the cumulative distribution functions for the Newsvender problem we looked at earlier. And these are for different order quantities. X, you know, remember we looked at 72, 92, and different order quantities that the newsboy should acquire in the morning. And if you look at this, you see, for instance, maybe around here, if I look at, say, 500, and if I compare the decision x equals 72 versus x equals 92, it seems like there's some sort of monotone relationship as we over here, okay? So it seems like if I look at the distribution function at a particular s, say being 500, for instance, for a particular cumulative distribution function for a particular x, say 72, and compare it with the distribution function for another x, say x hat maybe is, I don't know, 132, at the same s, say 500, we see indeed we're going to have that the probability associated with that the s is lower for one decision than another. And that is the situation that we have here. But you see, if we go a little higher up here, if I go, for instance, up to maybe even like 1200 or something like that, now you see that the blue line that used to be the lowest suddenly becomes the highest, okay? So now we don't anymore have this inequality. Now the one that was the best is not the best anymore. It doesn't have the lowest probability. So this is a situation where we do not have stochastic dominance between, say, for instance, the decision 72 versus the decision 152. Because for all the order quantities on the horizontal axis, it's not that we have one distribution function below the other. So this is where we do not have stochastic dominance. So unfortunately, in a way, as you can imagine, stochastic dominance is not something that we often might have in this sense, sort of in a practical setting. But what we might want to have, maybe you have some sort of a target distribution, and you somehow want to do better than that. Okay, so maybe you can finesse yourself better than some sort of a target distribution. So this is what we call first-order stochastic dominance. When we look at distribution functions like this, one can also do second-order stochastic dominance, which is a little bit more complicated function. You integrate up distribution function, and basically in economics, in finance, talk about expected shortfall. But basically, this has to do with what we call superquantiles or conditional value at risk in finance. Is basically if you can have for every probability level of a superquantile, we have one random variable it being better than the other, then you have a stochastic dominance of the second order. So that would be another way of comparing the distribution function. Again, you're in the same situation where you might very well find yourself with a situation that the two alternatives that you're really looking at, one doesn't dominate the other. Whatever the situation might be, if you try to do this, for instance, in a Newsvender problem or any other problem, what you get into is semi-infinite optimization. And what's semi-infinite optimization? Semi-infinite optimization is a situation where you have a finite number of decision variables. In the Newsvender problem, you have only one decision, x. And you have an infinite number of constraints. Okay. And where the infinite number of constraints coming from, that is from the fact that you have the desire to have these distribution functions, the relationship between distribution function hold, not only at one, what's called S here, which was the randomness, in this case the demand, but actually for all the demand, okay? So you would like to impose the constraint for all the different demands, okay? So that gets you into business with an infinite number of constraints, which of course at first might seem, well, this can get a little tough, but you know, people are working on methods for handling that. So it's not like something you automatically should rule out, but it has this additional complication. Okay. One thing that I think in this first slide deck I'm going to say something about is what about the effect of changing the probability distribution? Okay, I was somewhat confident when I started out, say, oh, let's do the log normal for this news vendor problem. And I said, well, by the way, you'll see on Thursday how we can figure this out. Well, I have to admit, even on Thursday, this issue is not going to be settled. Trust me on that. So the fact is, there's obviously an issue about what would be an appropriate demand distribution. And in a way, think about this. We are actually now at a higher level of concern, I will say. Remember where we started out today. We started out with a deterministic optimization problem, and we tried to make a decision about it without accounting for uncertainty at all. Okay? Then we worked hard and started developing a model of uncertainty, maybe 1 million scenarios in the product mix problem, or a log normal distribution in the news vendor problem, or whatever the situation. We developed a model of uncertainty, and we made a decision, and we got a decision, and in some very specific sense, they were better than what we had in the deterministic approach. So we already made progress from the deterministic, okay. Now, you're in a way asking me an even tougher question. In some sense, what is the uncertainty in the model of uncertainty, right? So in a way, we're now talking about second order effects in a conceptual, roughly speaking way. So you can pat yourself on the back that we already made some progress. We accounted for uncertainty. We obtained better decisions. And maybe that's all what's needed, okay? But of course, we shouldn't dismiss the fact that the model of uncertainty is going to influence our decision. But I will make the claim that often a crude model of uncertainty, meaning that even in somewhat incorrect probability distribution, will still get you decisions that are better than the deterministic ones, okay? But still, that doesn't mean that we shouldn't try to account for the fact that the models of uncertainty that we might have are themselves somewhat uncertain. And they, of course, could have important, I said secondary effect, but of course, it could be a significant effect nevertheless. For instance, just look at a small illustration here, which I think this is a good case scenario. I started out and worked with a log normal with mean 90 and standard deviation 36. And we got a solution that I think was 92, not 99. Suppose we change the story and change the expected value with 10% up to 100, and the standard deviation is slightly increased, I guess, with 10% as well. So basically, we made a 10% change in the distribution we assume for the demand in news vendor problem. Question is, how much does the optimal solution change? Well, in this particular numerical example, it changes up to 102. So it goes from, I think this was 92 to 102. So it changes with 10%. It was proportional to the change in distribution. This is, of course, a little bit of a coincidence, but it's a 10% change in the solution after a 10% change in the distribution in some sense. Of course, a very important question is, can we construct algorithms and procedures that are robust to these type of contaminations of the distribution, that you have incorrect distributions, okay? And one thing that I'm going to talk a little bit about on Thursday, that often optimal solutions might be somewhat sensitive to changes in distribution, more than what's alluded to here. And here, of course, we have strict concavity and things like that. These are factors that would help us to have a pretty stable solution. But generally speaking, you might have multiple optimal solutions, and you have a small growth as you move away from the optimal solution. These are situations where changes in distribution have a rather dramatic effect on the decisions. So one point I want to make on Thursday is that maybe look at things like near optimal solution might be fundamentally better if you want to have more stable with respect to changes in the probability variable. Of course, much interesting research is ongoing, and you'll see much of that in this conference, I think, about what is the effect of changing the probability distribution as well. Okay, so I'll make a few comments about where you can get more resources. In particular, I would like to highlight you to this recent book on modeling with stochastic programming. If you're interested in seeing how one can build up models, this is a good source in addition to these excellent references that focus on different aspects. Also, if you're not familiar with it, I guess this should be Stoprog webpage. There's a lot of tutorials there which have much of the same message that I've been conveying here. And in terms of how should I make a decision under uncertainty? Should I do the expectation? Should I maximize the expected profit? Or should I deal with stochastic dominance? Or should I somehow bring in utility? Or what should I do? We try to explain the different things and different options you have in this paper in a kind of practical way. So that could be another resource if you're interested in that aspect about how to capture the decision-making process under uncertainty. Okay, so I'm at the end of the first slide deck, and I don't know, I can switch to the second one if you like, because we still 5 more minutes. Should I do that, or would you like to have the break now? Okay, so why don't we just take a break now, and then we will get back. We'll continue with the second half.
IMPA 1, 2, and 3 to have a better distribution of the user. So it's the same password, but the name changed.